This is a Hewlett-Packard 8640B signal generator. It was built in 1977, and sitting atop it is a Hewlett-Packard 11710B down converter, which extends its range down to 10 kilohertz. And this particular HP8640B has the doubler in it, which will take it up to 1024 megahertz. And it's on that range at the moment. And what I'm going to do is just do a little bit of a demonstration of its warm-up drift. It actually is specified after 2 hours warm-up. I just wanted to see how it actually drifted in the first few minutes of switching on. So this is cold, hasn't been switched on today. Got the spectrum analyzer set to a center frequency of 768 megahertz, and which is sort of mid-range on this particular range on the signal generator. So let's see what it does. No modulation on at the moment. It's minus 30 dBs. It's going through the direct feed through this down converter. There's a little bit of loss in there of a dB or so. And these cables aren't the best either. Set the level to about 0 on the meter. Big deviation there. Sorry, amplitude is minus 31, which is probably about right for the losses in the cables and the box. There's a couple of coaxial relays in there. So we switch it on. It's at 767.978. I can increase the resolution of the display by switching the expand button here. I'll just tune it to the center frequency, roughly there. And see how it drifts. So it in this overflow position, it skips the initial digit. So it's 768 megahertz. The lock isn't on. This is a phase lock system, which increases the stability quite a bit. It'll correct for variations in frequency of the master oscillator by up to a couple of hundred parts per million. I expect this to drift down in frequency as the cavity and the electronics warms up. I'd expect the cavity to expand slightly, and therefore the frequency would drop, which I think it's doing. And these are tens of hertz. Which for an analog signal generator, which is being doubled because I'm doubling the oscillator frequency. That's the fundamentals in the 256 to 512 megahertz range. So 384 megahertz is the cavity frequency, and then there's a doubler circuit in here which is producing the higher frequency of 768. So it is drifting downwards. You can see that on the spectrum analyzer, which has got a 100 kilohertz span. I'll just reduce the span to say 25 kilohertz. And see it dropping there. So from switch on, it's dropped about 5 kilohertz, I think. Interestingly, the manual specifies drift after 2 hours warm-up. So I guess you don't expect this to be switched on and be accurate right away. Unlike modern synthesized generators, which require very little warm-up time at all. But I think this tells the tale here that you really got to leave this thing switched on, particularly if you're using it at the higher frequencies. If you're using it at the low frequencies where the fundamental frequency is divided by 2 on every range, it'll be pretty stable on the lower ranges fairly quickly, but on the higher ranges it will drift quite a bit. And after 2 hours warm up, it less than 10 parts per million, which is 8 kilohertz per 10 minutes, which isn't that good. But if you then click in the phase lock, which locks it to a 5 megahertz standard inside the signal generator, that 8 kilohertz drops down to 40 hertz in per hour. So that's it really does increase the stability quite a bit. And when I've been using it, I've noticed that it's very, very effective. And for an analog signal generator, that's excellent. Let's see how it's doing. Ooh, it's trundling down the scale there. 10 kilohertz or so. Yeah, it's quite a bit of warm-up drift. But I've used this signal generator on and off for the last month or so. Well, I've been doing some repairs on it, and it's been on for several hours at a time. And I know certainly after an hour or two, it's very, very stable. Increase the span to say 50. And it's now at 767 or so, which is confirmed by the counter in the signal generator itself. So I guess it does need an hour or two warm up to get this thing stable, particularly if you're using it on these higher bands, and this is doubling the error in the oscillator. So the oscillator it's drifting half as much as you can see on the spectrum analyzer here. Anyway, I'll leave it switched on, and I'm going to give another demonstration, maybe an hour's time, of the FM deviation, peak deviation settings, and it sort of goes along with a little short video I made earlier of how the mechanism of compensating for the divide by 2 on the frequency is compensated by the peak deviation switching and the little differential gears in there, which is quite a novel method of doing it. Anyway, I'll leave this switched on and let it stabilize, and I'll make another video shortly.